Welcome, health data pioneers, to a vital mission in our machine learning expedition. I'm thrilled to be here with you. And today we're tackling a classification task using an interpretable model from the Interpret library. I'm running this in Google Colab, breaking it down into clear code blocks so you can follow along as we explore a dataset about stroke risk. Let's get started by setting up our environment and gathering our tools for this life-saving analysis. I begin by installing the Interpret library in Colab with pip3 install interpret. This library is our gateway to explainable AI, helping us understand our model's decisions with precision. Next, I import the essentials: pandas for data manipulation, NumPy for numerical operations, and matplotlib's pyplot for potential visualizations, though we'll focus on Interpret's built-in plots. From sklearn, I bring in train-test-split to split our data, and F1 score and accuracy score to evaluate our model. I also import random oversampler from mblearn to handle data imbalance. And from Interpret, I import explainable boosting classifier from the Glassbox module, our star model for today, along with the show function to display explanations. I set up inline visualizations with set visualize provider and inline provider, ensuring our plots render directly in Colab. With our toolkit ready, let's load the data. I load the dataset using pandas read_csv, pulling in the healthcare dataset stroke data.csv file from my systems datasets folder. I print dataset.head to take a look. The first row shows a 67-year-old male, hypertension 0, heart disease 1, ever married yes, work type private, residence type urban, average glucose level 228.69, BMI 36.6, smoking status formerly smoked, and stroke 1, indicating a stroke. The next row shows a 61-year-old female, average glucose level 202.21, BMI NAN, stroke 1. This dataset contains 5,110 records of patients, with features like age, gender, health conditions, lifestyle factors, and a binary target, stroke, where 1 means a stroke occurred, 0 means it didn't. Only 249 patients had a stroke, about 4.87%. Making this a highly imbalanced dataset, which we'll address later. Let's pre-process it to get it ready for modeling. I check for missing values with dataset to send out some ID, gender, age, hypertension, heart disease, ever married, work type, residence type, average glucose level, smoking status, and stroke all have 0 missing values, but BMI has 201, around 3.9% of the rows. I drop the ID column since it's just an identifier, using dataset.drop with axis 1 and in place true. To handle the missing BMI values, I calculate the mean BMI, 28.89, 3237, and fill the nans with this average using FILNA, ensuring we don't lose data while keeping BMI realistic. Next, I identify the categorical columns: gender, ever married, work type, residence type, and smoking status, using select types with include object. I apply one-hot encoding with pd.getDummies, creating binary columns for each category, prefixed with the column names, and cast integers. I concatenate these encoded columns with the dataset and drop the original categorical columns, transforming the dataset into 21 features, all numeric, ready for modeling. I split the data into features and target. X is all columns except the last, stroke, and Y is the stroke column. I use train-test-split to allocate 20% for testing and 80% for training, with random state 2021, giving us 4,088 training samples and 1022 test samples. Given the stroke imbalance, only 4.87% positive, I apply oversampling to the training set using random oversampler with sampling strategy minority. I convert XTrain and YTrain to NumPy arrays, oversample to balance the minority class, stroke 1, and convert back to pandas data frames and series. This ensures our model isn't biased toward the majority class, stroke 0, improving its ability to detect stroke cases. We're now set to train our model. I initialize the explainable boosting classifier, or EBC, from Interpret's Glassbox module, with random state 2021 for reproducibility. EBC is part of the Explainable Boosting Machine, EBM, framework, which combines boosting, iteratively improving weak learners with interpretability. Unlike traditional boosting models, EBM uses generalized additive models plus interactions, GMs, fitting simple functions for each feature and their interactions, making it highly transparent. EBC is designed for classification, predicting binary outcomes like stroke risk while offering clear explanations. I call fit on xtrain and ytrain to train the model, and it prints training finished. I make predictions on xtest with predict, storing them in ypred, and evaluate with F1 score, macro average, and accuracy. The results: F1 score is 0.4867, a moderate balance of precision and recall, but low due to the imbalance challenge. Accuracy is 0.9481 to 94.81% correct predictions, but likely skewed toward the majority class, stroke 0, as only 50 test samples are stroke cases. I explore the local explanation for the first 100 test samples, calling EBM.explainLocal on xtest slice 0 to 100 and ytest slice 0 to 100, named EBM. I extract the explanation data for the first record with local explanation.data, 0, and print the details. Predicted 0, no stroke. True label 0, no stroke. Correct. Feature contributions show age at 1.526. The strongest positive push toward stroke, indicating older age increases risk. Smoking status formerly smoked at 0.233 and work-type children at 0.104 also push toward stroke, while average glucose level at -0.100 and hypertension at -0.052 pull against it. Interactions like age and BMI at 0.100 and age and average glucose level at 0.068 boost the score. On screen, you're seeing the local explanation plot, a bar chart for this prediction. The age bar stretches far right in orange at 1.526, driving the stroke prediction. Smoking status formerly smoked, also in orange, adds 0.233. Average glucose level, in blue, just left at -0.100, countering the prediction. Smaller bars like age and BMI in orange at 0.100 show interactions, with the final prediction of 0 marked at the top. A clear view of why the model chose no stroke. I move to the global explanation with EBM.explainGlobal, named EBM. I extract the global feature importance data with global explanation.data and print the values. Age leads at 1.133. The most influential feature. Work-type children follows at 0.180, BMI at 0.173, and average glucose level at 0.130. Hypertension is 0.095, while gender female and gender male are low at 0.002 each. Interactions like age and BMI at 0.132 and age and average glucose level at 0.098 are significant. On screen, you're seeing a feature importance graph. The age bar towers at 1.133 in blue, stretching far right. Age is the key driver of stroke risk. Work-type children at 0.180, BMI at 0.173, and average glucose level at 0.130, all in blue, follow. Smaller bars like hypertension at 0.095 and smoking status formerly smoked at 0.081 show their roles. Interaction bars like age and BMI at 0.132 highlight how feature pairs refine predictions. This plot confirms age, BMI, and glucose levels is critical for stroke prediction across the dataset. Let's reflect on these outputs. They're a health diagnostic for our model. The head showed a 67-year-old male, average glucose level 228.69, BMI 36.6, stroke 1, high risk. Missing BMI values, 201, were filled with a mean 28.89. After encoding, features like gender male, ever married yes, and smoking status formerly smoked became binary. F1 score 0.4867 reflects the challenge of detecting strokes, while accuracy 0.9481 is high but skewed, likely missing many of the 50 stroke cases in the test set. The local explanation correctly predicted 0 for a true 0, with age 1.526, pushing toward stroke but average glucose level minus 0.100, and hypertension minus 0.052, pulling against perhaps a lower glucose level reduced risk. Globally, age's importance of 1.133 aligns with medical knowledge. Older age is a major stroke risk factor. BMI at 0.173 and average glucose level at 0.130 reflect their roles, while interactions like age and BMI at 0.132 show how age amplifies BMI's impact. EBC's transparency lets us see exactly how these health metrics shape stroke predictions. To wrap up this critical health mission, we've analyzed the stroke dataset, a 5,110 patient study of stroke risk, and trained an explainable boosting classifier, achieving an F1 score of 0.4867 and accuracy of 0.9481. Oversampling helped, but stroke detection remains challenging. The local explanation showed age driving a no-stroke prediction, tempered by glucose levels, while the global view confirmed age, BMI, and glucose as key risk factors. EBM's interpretable approach, breaking predictions into additive contributions, makes EBC a powerful tool for classification, balancing accuracy and transparency. Grab this code, tweak this sampling strategy, and explore stroke risk further. I'm inspired by this health-focused dive. Hope it's got you thinking about data's impact on saving lives. See you next time for another impactful analysis.